In a universe filled with shining stars and tranquil orbits, there are phenomena whose power defies human imagination. Out there, in the black depths of space, impulses and catastrophes are born, capable of shaking the very fabric of space and time. What if what seems distant and unreachable is already affecting us, silently, invisibly, inevitably? We will look into places where energy exceeds all earthly limits, where planets collide and stars die in fiery bursts. This isn't science fiction, it's part of a reality that science is only beginning to comprehend. Subscribe and leave a like if you want to discover which cosmic forces are already guiding our path through the silent universe. Cosmic rays are elementary particles, photons, and atomic nuclei traveling through space at high energies. The majority of them are protons, 92%, followed by helium nuclei, 6%, with about 1% consisting of heavier elements and another 1% made up of electrons. The most intriguing are ultra-high-energy cosmic rays, extremely rare particles whose energy exceeds the Greisen-Zatsepin-Kuzmin (GZK) limit of 5 × 10 to the power of 21, determined by their interaction with photons of the cosmic microwave background. One of the most famous incidents occurred on October 15, 1991, when a cosmic shower was detected at the Dugway Proving Ground in Utah, triggered by a particle with an astonishing energy of 3 × 10 to the power of 20 electron volts. The detection was made using the Fly's I-HIARS instrument, operated by the University of Utah. This particle, nicknamed the "Oh my God" particle, had a kinetic energy equivalent to 48 joules, the same as a 142-gram baseball, traveling at 93.6 kilometers per hour. In 2021, the scientific community's attention was once again drawn to an event of comparable magnitude. On May 27th, a cosmic ray with an energy of 244 exa-electron volts was detected, the third highest ever recorded. The particle was named Amaterasu after the Japanese sun goddess, highlighting its mysterious and enigmatic origin. Professor Toshihiro Fujii, one of the researchers involved in the observation, admitted he initially doubted the accuracy of the measurements. The recorded energy level was that extraordinary. These rare particles may hold the key to understanding the most extreme and unexplored processes in the universe. How often does Earth face threats from space? And can we ever be truly prepared? What secrets lie hidden in the traces of ancient impacts that altered the course of evolution on our planet? Impact events are collisions between astronomical objects that cause measurable physical, geological, and biospheric consequences. These events regularly occur in planetary systems and are most often associated with the fall of asteroids, comets, or meteoroids. Although most of them have minimal effects, large bodies impacting terrestrial planets, including Earth, can be devastating. The minimum impact velocity for such objects entering Earth is 11.2 kilometers per second. The atmosphere partially mitigates the effect upon entry, but even so, many large objects retain enough energy to reach the surface and form impact craters, one of the most common surface features found on bodies in the solar system. Major collisions have played a significant role in the history of both Earth and the entire solar system. One of the most striking examples is the Chicxulub event, which occurred about 66 million years ago. It was caused by a massive asteroid approximately 10 kilometers in diameter that came from beyond Jupiter's orbit. It struck the area of the present-day Yucatan Peninsula, leaving behind a colossal crater. The consequences of the impact were catastrophic. Around 76% of all animal species, including most dinosaurs, went extinct. This event marked the end of the Mesozoic era and opened the evolutionary path for mammals. Another example is the Chelyabinsk meteor event, which occurred on February 15, 2013. A meteor, about 17 to 20 meters in diameter, weighing up to 13,000 tons, and with a density of 3.2 grams per cubic centimeter, entered the atmosphere at a speed of 18.6 kilometers per second and at an angle of 15 to 17 degrees. It exploded in the dense layers of the atmosphere at an altitude of about 27 kilometers. The series of explosions had a yield of 500 kilotons in TNT equivalent. The atmosphere absorbed most of the energy, but the shockwave spread up to 90 kilometers, affecting 11 municipalities in the Chelyabinsk region. Fragments of the meteor fell over a large area, including near Lake Chebarkul. Hundreds of thousands of people across 5 Russian regions and northern Kazakhstan witnessed the flash and shockwave, and dashcam recordings became the primary source of documentary evidence. Impact events have not only shaped evolution, but remain a current threat. According to NASA experts, preparing a mission to intercept an asteroid would take at least 5 years. However, on September 26, 2022, humanity carried out the first successful experiment to alter an asteroid's trajectory. The DART mission shortened the orbital period of the target body by 32 minutes, exceeding the target value, 73 seconds, by nearly 26 times. Could a single star passing nearby completely destroy the solar system? What would happen to Earth if its orbit suddenly changed? And is there a chance we could be consumed by another star? Scientists ran 12,000 computer simulations to assess how a flyby of a rogue star could affect the solar system. The probability of such an event occurring within the next billion years is about 1%. If the star passes at a distance of 100 astronomical units, there's a 95% chance that all planets will retain their orbits. However, even a minor disruption, such as the ejection of a single planet, can destabilize the system. Orbits become more elongated and tilted, and the overall system loses its stability. In some scenarios, Mercury falls into the Sun within 10 million years, while Uranus and Neptune are displaced, leading to a collision between Earth and Venus. In other cases, Saturn and Uranus are ejected, and in the most extreme scenarios, nearly all planets are lost. In one version, Earth is captured by the passing star, which has a mass nearly equal to that of the Sun. Jupiter remains, while the other planets either collide with the Sun or are ejected from the system. Earth's orbit becomes unstable, triggering drastic climate changes, though such an outcome is extremely unlikely. Most runaway stars, such as Kappa Cassiopeiae, pass by without posing any threat to the solar system. What happens to a star when it dies? And how does that affect everything around it, including Earth? Could rare explosions in distant space be the origin of the substances that make up our planet? A supernova is a stellar explosion in which the star's luminosity increases by millions of times. These explosions are accompanied by powerful emissions of radio waves, X-rays, and cosmic rays. Some gamma-ray bursts are also associated with this phenomenon. During the explosion, supernovae eject heavy elements that form the matter of Earth and other bodies in the solar system. These elements remain in the interstellar medium after the expanding shell of the supernova remnant dissipates into space. Historically, only 7 supernovae were recorded before the 17th century. The most famous is the one from 1054, whose remnants are now visible as the Crab Nebula. The last bright supernova, SN 1987A, was discovered in 1987 in the Large Magellanic Cloud at a distance of 160,000 light-years and became visible to the naked eye. The explosion mechanism involves the outer layers of the star collapsing onto its core, rebounding, and forming a shockwave that ejects matter outward. If the core's mass exceeds 3 solar masses, it does not form a neutron star, but instead becomes a black hole, a region from which not even light can escape. Why did the first ever observation of a kilonova challenge fundamental astrophysical models? What did scientists see in the fireball that no one expected? A neutron-star merger is a rare type of stellar collision that results in some of the most powerful cosmic catastrophes. In 2017, the gravitational wave event GW170817 was recorded for the first time in history, caused by such a merger. It was accompanied by the flash AT 2017 GFO, the first direct and compelling example of what is known as a kilonova. This event confirmed theoretical predictions that neutron star mergers produce heavy chemical elements, including gold and strontium. Moreover, AT 2017 GFO became the first observed kilonova, allowing scientists to study the structure and dynamics of the ejected material in detail. Until recently, it was believed that material in such cataclysms is ejected in a flattened and asymmetric cloud. However, a study led by Albert Sneppen from the University of Copenhagen challenged this view. Based on emission and absorption spectra of strontium plus in the first days after the flash, obtained using the X-shooter spectrograph on the VLT telescope, it was established that the ejector had an almost perfectly spherical shape. The data showed that the photosphere expanded spherically symmetrically, and the distribution of strontium plus closely matched this geometry. This contradicts existing magnetohydrodynamic models, which suggest that the early stages of mergers are characterized by pronounced asymmetry. Scientists considered all possible energy sources and configurations, from the radioactive decay of heavy elements to winds from a magnetized neutron star and jets around a forming black hole. But none of the models could satisfactorily explain the observed symmetry. At 2017 GFO not only confirmed the formation of heavy elements, but also revealed serious gaps in current theories, leaving scientists facing an unexpected discovery that calls into question our understanding of neutron star merger processes. What is hidden within one of the most powerful magnetic fields in the universe? How could a single cosmic explosion outshine the full moon and release more energy than the sun emits in 100,000 years? Magnetars are neutron stars with extremely powerful magnetic fields, reaching up to 10 to the power of 11 Teslas, trillions of times stronger than Earth's. These objects are capable of releasing enormous amounts of energy in very short periods of time, surpassing even typical supernova explosions in brightness. One of the most well-known magnetars is SGR 1806-20. Located about 50,000 light-years from Earth in the constellation Sagittarius. On December 27, 2004, a massive energy outburst occurred on its surface. The burst was so powerful that its gamma radiation, upon reaching Earth, briefly outshone the full moon. In just 0.1 seconds, the magnetar released as much energy as the sun emits in 100,000 years. Approximately 1.3 times 10 to the 39th joules. This event became the brightest cosmic explosion in our galaxy since the supernova observed by Johannes Kepler in 1604. Another example is SGR 1900+14, located 20,000 light-years away in the constellation Aquila. After a relatively quiet period, it suddenly became active between May and August of 1998. On August 27, 1998, a powerful outburst occurred, so intense that the near-Shoemaker spacecraft was automatically shut down to avoid damage. Later, on May 29, 2008, NASA's Spitzer infrared telescope discovered rings of matter surrounding the magnetar, likely remnants of the 1998 flare. Magnetars remain among the most mysterious and energetically intense objects in the universe, capable of affecting spacecraft even in Earth's orbit. Every step in exploring space reveals new horizons that raise more questions than answers. From the most powerful collisions to the greatest cosmic catastrophes, these events show us how fragile the world we live in can be. Understanding cosmic processes not only uncovers the mysteries of the universe, but also helps us grasp the scale and potential threats that could alter our course. Subscribe to the channel and stay tuned for the most exciting and important discoveries about the universe and its incredible phenomena.